Okay everybody, in this video we're going to talk about 12.3 regression equations. And so if you recall in the last video we looked at scatter plots and we talked about correlation and what a strong or weak linear relationship looks like. And we talked about this line, all right, which goes by a couple different names. The line of best fit, it's a regression equation. We're going to talk about how to find that line. How do we find the line using StatCrunch that best approximates all the data we have? Because then we'll be equipped with some sort of a formula that I can then use that formula to then go and answer more questions or make predictions about things in the future. Okay, so let's just get a little bit of terminology out of the way. So first of all, our x value. Our x variable can go by many names. The predictor, the explanatory variable, the independent variable. Sometimes you hear people call it input if they're talking about function notation. So all of those things are referring to the x value, or the the input of your equation or your function. And the y value, the y variable, goes by fewer names, but it's got a lot of options. Sometimes it's referred to as the response variable, the dependent variable, or sometimes the output. So you'll see different people in different books use different terms, but they're all describing either the x value or the y value with those terms. Okay. So before we get into how we do this, let's remind ourselves the general form of a linear equation. And so here it is. It's the same thing I wrote up there. If you recall, m is the slope of the line and b is the y-intercept of the line. And this is the general formula for any linear equation, y equals mx plus b. Now, what we are going to do is, again, let the computer do the tedious work of figuring out, okay, for all of these lines, it looks at how much, it tries to place the line so that it minimizes all these distances. So it makes every point as close as it could get to the line. Okay, it's going to move the line up and down and adjust the slope until it can find that best fit there. So what's going to happen is the computer is going to crunch the numbers and they're going to give us some values. They are going to tell us the slope and the y-intercept for this regression line, also known as the least squares regression line. Least squares because that's the method that's being used to generate the line. All right, and again, it is the line that best fits the data in the scatter plot that's comparing these two values, the independent variable and the dependent variable. Now, our line has the equation y equals mx plus b, but you could use different letters, right, for m and b. I mean, 99% of the algebra books you're going to look in, that's what they call them. But there's nothing special about M and B. Some books, some programs use this. Now it could be confusing because look, they're using B, but your slope is the thing that is multiplying your x value. So here the B is the slope, okay? And the value that is all by itself is your y-intercept. So here they're using A. So maybe a better way to think about this in general, so it doesn't matter what letters a book uses, is you could think of y is always equal to your slope times x plus your y-intercept. All right, no matter what they want to call it, what letters they want to use, that's the format for a linear equation. Now there's something else different here, and it's really important. Do you notice they put a hat over the y? Okay, that's really important to include that because what we are getting from the computer is not a line that 100% captures all these data points. You could see from the quick picture I drew, some of these data points are above the line, some are below the line. This line is approximating the data points, and to symbolize that it's an approximate linear equation for that relationship, we use the hat symbol. If you do not use the hat symbol, like here, then you are implying that this formula dead on generates all of those data points, and every single one of those data points should work in the equation. That's not going to happen for our approximating line, right? Our regression line. It will not actually contain all of these points. You know, pick a point like this guy. If I were to plug in its x and its y value, these two sides of the equal sign would not be equal because this isn't on the line. But they'll be really close because, again, this line is just approximating the data. It's not actually describing it 100% accurately. So when you're dealing with a regression equation, use the hat notation so that the reader and yourself know that you're just talking about an approximating equation. Okay, so it's really easy to do with technology, and there's free programs out on the internet that will do it. StatCrunch will do it. Your graphing calculators will do it. So it just, depending on the problem you do, the program you're using, it may look a little different or be a little bit different on how you do it. For all of them, though, what you're going to need to do is first enter the data. Enter the data pairs into your calculator or StatCrunch or whatever, and make sure that the order of your data corresponds with one another. So you don't want to scramble up the x and the y values, okay? On StatCrunch, you're just going to go to Stat, Regression, Simple, Linear, and then it's going to spit out a whole bunch of stuff. What you need to find is what are they estimating the intercept at, and what are they estimating the slope at. And actually, I don't even think they use this notation. I think it uses A and B, but I'll have to double check. We'll see in a minute. They also just flat out write the equation for you, and I'll show you where to find it in StatCrunch, okay? So on the next page, they give us an example. This is talking about how software other than StatCrunch may use different names and labeling, and again, there's always a slightly different way to do it depending on what bit of technology you're using, but they're all doing the same thing. So let's take a look at this data here. What we've got is scuba divers have a max dive time they cannot exceed when going to different depths. The data in the table below show different depths with the max dive time in minutes associated with them. So when you are diving down to 50 feet deep, you can stay down there for up to 80 minutes at 50 feet. As you increase your depth, so if you go down to 60 feet, now you can't stay down as long. You can only stay down 55 minutes, and so on, all the way through to the very end, where if you're down there for if you're down at a depth of 100 feet, your dive time is only 22 minutes. So they have gone ahead and chosen the independent and dependent variables for us, the x's and the y's. And so what we've got is depth for my x value, dive time for my y value, and just thinking about it, I think we're going to have a negative correlation going on, because as the depth is increasing, as you go deeper and deeper and deeper, you get closer to 100 feet, we see the dive times going down. They're getting lower and lower. So the data values would probably look something like this, okay? And our job right now is to graph it and try and figure out what is the line that does its best job at approximating those data values, and how strong or how good of a job does it do. So that's another thing StatCrunch will tell us, is not just what is the equation of that line, but how good does it do. So they ask us to use StatCrunch to go find the least squares regression line, and then use that to make a prediction about your dive time for 110 feet. And again, that's the beauty of finding this equation, because if I wanted to get my dive time for a depth of 110 feet, well, that data value isn't provided. They don't give me that data value here, right? And so the best I can do is kind of use the pattern I'm seeing, build an equation that sort of predicts that pattern or that trend, and use that equation to find my dive time. So I went ahead and already loaded these values in StatCrunch, so just to save a minute, let me show you that. So what I put the depths, and I put the dive times, and again, I didn't mix them up. Make sure each depth goes with each correct dive time, okay? So I'll do two things. I'll go ahead and you know what? Let's just graph them real quick. So what's the x variable? Depth. What's the y variable? Dive time. And I labeled them x and y too to help me. Let's just look at the graph real quick. So that's what we kind of said. Look, we've got sort of a downhill trend, a negative correlation, and it does to me look linear, right? It looks like it makes a line more so than exponential decay or anything like that. So we want to find the line that fits that data as best it can, and we want to see how strong it is. So how I do that is I go to Stat, I go to Regression, Simple Linear, because we think it's a line. If you thought it was some other shape, you would have options here, but Simple Linear. Again, tell it which column holds the x variables. That's the depth, right? The depth is the independent variable. Which column holds the y variables? That was the dive time. I don't need to touch anything else. Okay, we're gonna learn about some tests involved with this later on, but for now, let's just hit compute. Although I want to see the graph. Yeah, let me just hit compute, and I'll come back to this. All right, so it gives you a lot of information. Let me just go to the next page real quick, and I'll come back. There they show my data points, and there's the equation of the line they found. And if you hover your cursor on it, it tells you the equation of the line right there. Y equals 127.23 minus 1.114x. Right, I'm cutting off some decimals there, obviously. Let me go back. So a lot of this information is not needed for us. When we get into 12.4 and 5, we'll talk a little bit about this, but really what we need is, here's the equation again, right here. Dive time, y equals, there it is, that's what we found, right? And the other thing that's good to see is the correlation coefficient. So remember in the last video we said that a correlation coefficient is a number between -1 and 1. It's negative if the data is going downhill and positive if the data is going uphill. And the closer it is to those ones or negative ones, the stronger the correlation is between depth and dive time. This is really close to -1, meaning there is a strong correlation or a strong association between the depth that you scuba dive and the dive time you can stay there. Okay? So I'm just going to copy this equation. Again, one way to get it is just to hover over the graph and you can see it right there. I'm only going to take a couple decimals though. So 127.2 and 11.1. Let's just do that. I'm just going to go 1 or 2 decimals. So let's say that y hat, because again, it's not the equation that actually generates that line, it approximates that line. It was 127.2 minus 1.1x. I cut off a lot of the decimals, but it'll be close enough for our purposes. Okay. But again, that hat symbol says that I'm approximating this data. Once you're armed with that equation, you can go answer a variety of questions about this stuff. So they want to know, well, what's the dive time when my depth is 110 feet? If your depth, which is x, equals 110 feet, let's plug it in and see. Y hat, the approximate dive time, I'll give you a minute. I got 6.2. So you could stay down for approximately 6.2 minutes. Is that right? Yeah. Okay. It's just very different than what I had written down when I did this a while ago. So one of them must have been a calculator error. I think this is good. If you did this and you got a different value, maybe I typed something in or copied a data value wrong. But let's see. So at 110 feet, we can stay down for approximately 6.2 minutes. All right. Okay. So again, we're letting technology do all the work for us. So for us, it's as hard as typing in the data values and knowing how to generate that equation. Once you have the equation, it's a plug and chug scenario to try and to use it. So the other thing they talk about that we want to be aware of is this idea of residuals. What a residual is it is what we observed minus what we predict. All right, so residuals is observed minus predicted. All right, if that helps. Basically, it tells us how far off we are. So it tells us how far from an observed y value is the predicted y value based on a given input, based on a given x value. A residual plot shows all the residuals for the points around the regression line. So again, each one of these points is off, right? Every one of these points is a little bit off of the line. So the residual would be, well, how much is it off? It looks at each one and says, how much is it off? That's the residual. So let me go back to StatCrunch and put that feature on real quick. Let me go to options and let's, I want to see the residual index plot. I think that's the one I want. Let's see. Not quite what I was picturing. What they're showing here is the line 0 would be for if your data point was dead on. I have some values above the predicted and below the predicted, and so that's why I have some positive residuals and some negative residuals. So again, each one, if you hover on it, it's telling you the data value and how much it was off from what the line predicted. Okay, you can see the residual values there. Let me take a look at one more thing. That's not quite what I was looking for either. Anyways, maybe that other one was doing a better job of kind of giving us my values. So again, for every single one of those, let's put the histogram on too. For every single one of those residuals, so this is kind of looking at residuals in these categories and how many data points were off by that amount. Okay. Let me go back. So for each of these data points, again, this is not my data point. This is the residual of this first data point. Okay. So for the very first data point, row 1, all right, what I observed when I went down 50 feet is I observed a dive time of 80. They told me that it was off by 8.47. So what that means is if I were to plug 50 feet into my approximating equation, the one that StatCrunch told me, I would get an answer that is different than this answer by 8.47. It would actually be 8.47 below what was observed. Watch, let's go back to the notes and calculate one of these. So here it says, sorry, screen's a little laggy. Predict the maximum dive time for a dive with a depth of 60 feet. So we have that data value. They gave me that when you're at 60 feet, you've got 55 minutes of dive time. They want us to see what does our predictor do? What does our estimating formula do? So I want to use this equation. And maybe I shouldn't have rounded it so much, but it's okay as long as we get the idea. Let's see what that says when I go down to 60 feet. So if my depth is 60 feet, right, remember that's my x value, what I would get is I would estimate my estimated dive time would be that is not right. Hold on. Would be 61.2 minutes. That's my predicted, right? Okay. So it's off, right? Because I estimate, or the actual dive time I have is 55 minutes. This equation would predict it as 61 minutes. What was the observed max dive time? Observed time was 55 minutes, right? That's the max you could stay down at that depth. Calculate the residual and write it as a sentence. Okay, well, the residual is equal to what you observe minus what you predicted or estimated. So in this case, I observed a dive time of 55 minutes. I predicted a dive time of 61.2 minutes. So I got a residual of negative 6.2. Now, if I were to look at what it tells me on StatCrunch, it's not going to be exactly that because, again, I took off a lot of decimals here, but it should probably be close. Let's go see. So we're talking about 60 feet. So 60 feet, that's row 2. So look for the data point 2 down here. The residual is negative 5.38. Yeah, I got negative 6.2. That's off quite a bit. But again, I'm certain that's because I really rounded these decimals off, right? I left a lot out there. So if I was being a little more accurate, I'm sure I'd get a better answer. But that's okay. We'll run with it. So anyways, that's my residual. And so what that means is that the observed dive time was about 6.2 minutes below the predicted dive time. Okay. So it's important to understand how much you're off by because in this case it could be very bad to stay down longer than you're supposed to, right? Okay, again, if you run this on your own, take some more decimals there because then it's going to match the figures on StatCrunch too. I should have gone at least a couple more to get better answers. But I hope you got the idea. All right, last thing, let me look at the next page. Okay, so what this little blurb is doing is this is helping us to interpret the context of the slope and the y-intercept. Okay, so interpret what the slope and the y-intercept mean that the computer told us in the context of the problem, because the computer gives us a number. We want to interpret what that means. And I'm honestly a little slightly confused on what they're asking me to fill in here. So I just want to go do the example that we just did and let's interpret that. Okay, so let me again remind you from my equation what we found is we got 127.2 minus 1.1x, right? Or that was my my rounded version of it. So again, which one is the slope? The slope is the one that always multiplies the x value. So it's kind of written a little backwards than what you may be used to seeing. Usually we see the slope first. Well, addition is commutative. You can move it, change the order. So really look at who's multiplying x. The intercept, the y-intercept, is always the standalone number, right? So there's my y-intercept. So let's interpret these things. I have a slope of negative 1.1. Okay, the slope is negative 1.1. And so what do you think that means? Every time this increases, and what is this? This is depth in feet. All right. What it's hinting at is that every time you go 1 foot deeper, so as this number gets bigger by 1, you lose 1.1 off of this number. And this is your dive time, right? The whole thing is your dive time. Okay. So every time you go 1 foot deeper, you lose 1.1 minutes of dive time, all right, according to this. So every time, or you could say it a whole bunch of different ways, but for each foot in depth you gain, I guess, or for each foot you increase your depth, you would lose 1.1 minutes of dive time. All right. And what does the y-intercept mean? Remember, the y-intercept happens when your input or your x value is 0. So what that means is that you would have 127.2 minutes of dive time if your depth was 0. Okay. We predict 127.2 minutes of dive time if your depth is 0 feet. Now I want to just quickly highlight this. It says sometimes the intercept does not make sense in context, but you should still be sure to understand what it represents. And that's true. A lot of times the problem just doesn't make sense at the intercept. Sort of like this. I mean, if you're at 0 feet, you're not diving, right? You're basically at the surface of the water. So you could take that to mean that there's 127 minutes worth of air in your tank, okay? But it's also possible that you know, the y-intercept comes out to be a weird funky number, like a negative number, something like that. So, I mean, for example, maybe you've got all of your data doing something like this, and around this window, the line is doing a great job estimating your data, okay? But take a look at what I've just drawn. If you were to extend these axes, your y-intercept is occurring down here at some negative value. Well, depending on what these represent, maybe it makes no sense at all to talk about negative value. Like, for example, if this is time, like it is in our case, negative time wouldn't make sense in the context of this problem. Okay, so it's not unlikely for the y-intercept to be a little bit of a head-scratcher, to be sort of like, well, that's weird. Just make sure you understand how you could interpret it. Okay, that's it. That's it for this one. Take care, you guys.